Hello, welcome back. So in this case, in the previous four example, I have done the analytical type of problem in which we were required to find out the compressive strength of the member. Well, in this example, we will solve a design problem. Like in this problem, we are supposed to design a compression member. So there are some steps that we generally follow to design the compression member. So we will see first what are the steps that we generally follow to design the member, and then we will take an example to solve that. So in the steps that we generally use, first of all, what we do is we assume a suitable design compressive stress, which means first step is to assume the value of FCD. And for an idea, generally we assume FCD as 40 to 60% of the FY value, or we can say zero point 0.4 to 0.6 times of FY for an idea. So that is the first step that we generally do. In the second step, we try to find out the effective sectional area required. And effective sectional area required, we calculate this from this formula. So we know that PD is equals to AE into FCD. So we already assumed that FCD in step 1, and PD here, the PD means it will be already given in the question, the factored load. It will be the factored load for which we have to design the section. So here the PD value will be factored load, which will already be given in the question if it is a design type problem. So using this value, then we will calculate AE value, which will be the required effective area. Then in the third step, we will choose a section which gives effective area required, and then we will also calculate the R minimum, because R value can be find out from the steel table. So basically we will use steel table to select the section which will be having effective area around this area which we have calculated in the step 2. Then in the step 4, we will determine effective length based on the end conditions, whether it is a fixed condition or hinge condition. That on the basis of that we will find out the effective length, and then in the next step we will determine the slenderness ratio, and therefore we will find out the actual design stress. So this actual design stress will be for the chosen angle section. So once we find out the actual design stress, we will find out the load carrying capacity of the section that we have chosen from this step 3. So once we find out the load carrying capacity of the chosen section, then we will compare that with the factored load that is to be required to be supported. So if the load carrying capacity that we have calculated in the 5th step, if it is more than the required factored load, then we can say that the section is safe. But if it is less than that, or the difference is very large, in that case we redesign the section by taking another section from we will repeat all the steps from 3. Okay, so now we will check this from the example. Also, sometimes we are required to assume the slenderness ratio. Well, I have just shown you the process. Like in first step, we assume the FCD value as 0.4 times of FY to 0.6 times of FY. Well, this is one way. Another way is by assuming the value of slenderness ratio. Well, in case if we are using single I section, so it says that we can assume the lambda value approximately between 80 to 150. So for example, if I assumed the lambda value as 100, okay, and Fy value we already have as 250. So if we have lambda value 100 and Fy value is 250, then from the from the IS code, single I section belong to B or C class. So from table 9B or 9B, we can find out the value corresponding to this lambda. So this is again a way to find out the FCD value. Because initially, why we are required to find out FCD value? Because to estimate the effective area which will be suitable for the required factored load. So this process we will see in the example. So now I will show you the example that we are going to solve. So this is the example 5 in which we have to design a column to support a factored axial load of 1100 kilonewton. So we have to design a column which will support this 1100 kilonewton load. The column has an effective length. Well, effective length is directly given here. So the effective length is 6 meter with respect to Z axis and 4 meter with respect to Y axis. Well, there are two effective length along different axes. Well, as I said, for example, this is a column and this may be the Z axis, this may be the X axis, sorry, Y axis. So along the Y axis, this may be the effective length. Along the Z axis, this may be the effective length. So it says that along the Y axis, it is 4 meter and along the Z axis, it is 6 meter. Well, when this difference comes, because when the column is connected from this end, so in this end, the beam may have more depth, while in this case, if the beam is along this line, the beam may have low depth. So in that case, the effective length may differ because effective length is ultimately the clear, the clear length will be ultimately a difference between the floor level and the top, bottom of this beam level. Like if this is the column and if it is connected by this beam, so in that case, clear length of this column will be this one. And based on the connection, we will find out the effective length. So this is the clear length, which is L. So effective length along this axis may be different along than the other axis. So if column is connected from having the different depth of beam along this axis and along this axis it is different, in that case such differences occur. Okay, so now we will solve our question. So first step is about the assuming suitable design compressive stress. So generally we assume this FCD value between 0.4 Fy to 0.6 Fy. So assuming that we are taking 0.6 Fy and we already know that Fy value is 250 MPa. So we will assume that as 0.6 Fy as 0.6 times of 250, which means we are assuming that FCD value as 150 MPa. So based on this assumption, now we will follow the next step, which is about calculation of the effective area. So calculation of effective area is calculated using this formula. And in this formula, we are taking PD as the required factored load, which is 1100 kilonewton, and upon my FCD value. So FCD value is given in the Newton per mm square. So that is why we will convert this 1100 into Newton. So we will multiply this by the 10 raised to power 3. So I have already calculated this. So there you can see this is the effective area required for the column to support this. So now based on this area that we have calculated in this step, now we will look at the steel table and we will find out, we will choose a section which will be having area around this one. So generally we will take an area which will be more than this one. Okay, but it will be around this one. So in the next step, we will write a section is to be selected which gives effective area required, and then we will calculate R minimum. So first we will look at the steel table, and also we assume that we are going to design I section, because I sections are the most suitable section to carry heavy loads, because 1100 is a heavy load. So that is why we are going to select I section. And in I section, we are having option either we take IS MB or IS HB. Okay, so we have these options. So I will show you that table. How do we find out that? So area that we have to see. 7333. So if we convert this into centimeter square, this will become 73.33 centimeter square, because the area in the steel table is given in the centimeter square. So that is why I have converted directly here. So now, so in the steel table, you can see I section start from section 2. So first, if we look at the ISMB section, and in the third column, you can see sectional area. So we have to look at the area which will be having around 73.33. So these sections are not qualifying our expectation. If we look at more, ISMB 400 is having 78.4, which is a little more than the 73.33. So we will consider that if we are not able to find out in other options. So ISMB is not having the required area, which is around 73.33. So we will look at other sections like ISJB is the light beam. So here also ISLB 400, it is having a cross-section area 72.4, but it is less than 73.33. So that is why we are again not taking, not considering the ISLB. Similarly, ISWB may also have like this ISWB 350. It is having 72.5. Again, it is less than 73.33. So we are not going to take this one also. Then ISSC in this, generally these sections are not much used. They are basically heavyweight beam section. So in this case also, the sectional area is 76.8, which is again near to 73.33. So we can consider this also, but we will explore more sections like ISHB. If we consider the ISHB, in the ISHB you can see 74.8. It is very near to the section that we are required, which is 73.33. So we can adopt ISHB 300, which is 74.8, and we can write all the values from here. So D value, it is actually the H value. In the new code, we use H value in place of D. So for ISHB 300, which is having this area, so corresponding to this, we will write all the values: height of the column, the depth of the column, and width of the flange, thickness of the web, thickness of the flange, and similarly the moment of inertia, if it is required. I don't think it is required in our case. And yes, radius of gyration is also given here, which is 13 centimeter for RXX. So again, this RX is actually RZ. So as per the new code, which is IS 800 2007. So as per new code, we are using RZ in place of RX. And along the y-axis, it is 5.41 centimeter. So we will note down all these values in the from the steel table. So now we will be going on to the slide. So here, as I said, we will try ISHB 300, and all the relevant property we will note down from the steel table. So area is 7480 mm square. There it was given in centimeter square. I have converted that in mm square directly. Similarly, RZ value there given as Rx value, but I am writing here as RZ. So there it was written 13 centimeter. I have converted this into mm, which is 130 mm. Then Ry value. Then it was written as D value, but now I have written this as H value, which is 300 mm. And B is the width of flange. So I have noted down all the values. Similarly, the thickness of flange as 10.6 mm. So all these values are required to calculate various parameters. Then also, as it is written that we will identify which one is the minimum radius of gyration. So we can see minimum radius of gyration is along the Z axis, which is 54.1 mm. So now in the step 4, we will determine the effective length. Knowing the end conditions, well, actually effective length is directly given in the question. So along the Z axis and Y axis, it is already given. So we will write there. So now we will determine the slenderness ratio, because ultimately we have to find out actual design stress, which is FCD. for the chosen angle section, which is for ISHB 300. So for that, we will find out the slenderness ratio along z-axis and along the y-axis. Although we will adopt FCD value, which will be having minimum radius of gyration, but again we are calculating uh, lambda value for z-axis as well as for the y-axis. So lambda z will be effective length along the z-axis is 6000 mm and radius of gyration along the z-axis is 130. So in that case, lambda value is 46.15, which is again less than 180. So this 180 is given in table 3 of IS code. So you can check that. And along the y-axis, lambda y will be effective length is 4000 mm along the y-axis and radius of gyration is 54.1. So in that case, the lambda value is 73.94, which is again less than 180, which means our section is okay from the permissible limit of slenderness ratio criteria. So again, as I said, that minimum radius of gyration will give us the value of FCD. So generally, we can conclude that compression member is weak along the axis having least radius of gyration and higher slenderness ratio. So you can see along the y-axis, we are having least radius of gyration, and also along the y-axis, we are having higher slenderness ratio. So as I have already explained in the previous lecture, that if the slenderness ratio is higher, then the strength of the member will be lower. So the lower, the axis about which we are having higher lambda value, we will adopt that because that will be the critical one. So FCD value for the lambda y will be adopted, and also before calculating FCD, we have to check which table we have to look for. Whether we have to look for table A, 9A, B, C, D, we will be, it will be decided on the basis of buckling class. So we will check which buckling class our I section belongs to. So based on the table, table 10, we will find out H by B ratio, which is equals to 1.2, and then thickness TF, which is 10.6. So if H by B is more than 1.2 and TF less than or equals to 40 mm, then it belongs to the buckling class B. Well, here it is actually exactly 1.2, but still, as the thickness of flange is less than 40 mm, we can adopt our buckling class as B. I will show you that in the table also, how I am doing that. So there in the IS code, you can see if we refer to the table 10, and in table 10, we are supposed to find out H by B ratio. So in the case, we calculated H by B ratio as 1.2, and 1 second. So H by B ratio is 1.2 and thickness of flange, if it is less than or equals to 40 mm, then buckling can occur along the z-axis or y-axis, and buckling class along the z will be A and buckling class along y will be B. Similarly, if the thickness of flange is between 40 to 100 mm, in that case buckling class is changed. Along the z-axis it will be B and along the y-axis it will be C. Okay. Similarly, if the H by BF ratio is less than or equals to 1.2, but thickness is less than 100 mm, in that case, buckling class can be B or C. Well, technically our case should be like this, but in that case, this thickness is comparable, which is 100 mm. While in our case, our thickness is around 10 mm, which is less than 40. Well, if we check the accuracy, this result will be more accurate that we are going to adopt. So in this case, it says H by BF ratio is more than 1.2. Well, our value is exactly 1.2. So we can adopt this class because it will give us more accurate result, because in our case, thickness of flange is less than 40 mm. So that is why it will give us more accurate result as compared to this one. So that is why I'm adopting this class as H by BF ratio more than 1.2 and thickness of flange less than 40. So because of that, buckling class is along the z-axis will be A and buckling class along the y-axis will be B. So now I will be showing you that in the slide. So there I have written that H by B ratio as 1.2, thickness of flange as 10.6, which is less than 40 mm. So referring this table, we can find out the buckling class as B. And for buckling class B, we will refer to the table 9B. So I have already explained how do we find out FCD value from the table. So I am writing here directly. So FCD value can be calculated from the interpolation. So after interpolation, the value of FCD is 159.7 Newton per mm square. So now we found the value of FCD. So now we will find out the load carrying capacity of the compression member. So load carrying capacity of the compression member will be AE into FCD, and our adopted area for the ISHB 300 was 7480 multiplied by FCD, and the load comes out as 1194.5, while the required load which we were supposed to which is required to be supported was 1100. As per the question, we are required to select the section which will support this load. The load carrying capacity of the chosen section is 1194.5 kilonewton. So it is more than this. So we can say that the section that we have chosen from the steel table is safe. So we can say that ISHB 300, that's the section that we have chosen, is safe and it can carry the required load. Okay, so that was the solution of this design problem. So this is how we design the sections. Thank you.